In the previous video, we learned that there are two types of transformers based on the working principle. One is step-up transformer, another one is step-down. Step-up is V2 is larger than V1, I1 is larger than I2, P1 equal to P2 ideal case, or P1 is greater than P2 practical case. And number of turns on the secondary, N2 is higher than N1. That is for step-up. Step-down, N2 is less than N1. And V1 is greater than V2 and I2 is greater than I1. P1 equal to P2 ideal case. So ideal case, step up, step down, both of P is same on both sides. And practical case, P1 is higher than P2. Transformer is the one of the highest efficient electrical machine compared to the electrical motor and electrical generator, because there are no rotating parts in the transformer. Now that is based on the working principle. When it comes to the construction, there are two types of transformers. One is core type, another one is shell type. So a core type is nothing but there is a core like this, and primary and secondary, instead of calling them primary and secondary, we call them as high voltage and low voltage. Primary is connected to the source, secondary is connected to the load all the time. Okay, and LV or HV are nothing but high voltage and low voltage. When it comes to the any type, either core type or shell type, okay, always there is LV winding first, and then on top of it HV winding, half of it on one side and half of it on the other side. Okay, so both sides will have LV winding, HV winding, because it will give us a better magnetic coupling. So to have better magnetic coupling, always you can see in this picture right here, always there is LV winding right there, low voltage, on top of it HV winding, that is HV winding. Okay, we are viewing cross-sectional view, so we are cutting half of it, so on the side, and you're looking from the side. So you can see that's LV winding, HV winding, LV winding, HV winding. So half on one limb, half another limb. Okay, that is core type. Whereas shell type is nothing but you will have core on both sides of the coil. Okay, so both coils are in the middle. If you look at here, so coils are going to be in the middle. Magnetic field is going to be divided half on one direction, another half another direction. But LV winding is right here. This is LV winding, this is HV winding. Okay, so according to construction, there are two types of transformers. One is core type, another one is shell type transformer. When it comes to the power transformer, other transformers like unit transformers, which they don't step up or step down, they will supply or improve little bit of voltage to reduce the transmission line losses. Sorry, actually they increase the little bit of voltage to cover the voltage drop in the transmission line. Okay, those are the unit transformer. Substation transformers are step up and step down transformers. Distribution transformers are the other kind. Now for the measuring purpose, we use potential transformer to measure the voltage, and the current transformer to measure the current. Now as I mentioned, transformer is a high efficient machine. Even 5% losses is huge amount of power loss. That power loss is going to be that power loss is nothing but it's going to convert electrical energy into heat energy. Okay, so it produces lots of heat, transformer, and it is placed in a closed container. So small area, lots of heat, it will produce lots of heat. Okay, so to cool it down, there are different types of transformer based on the cooling. One is oil filled self cooled transformer, another one is oil filled water cooled transformer, another one is air blast type transformer. These are the different types of transformers. The next topic is transformer rating. Always the transformer rating is in kVA. okay, 100 kVA, 200 kVA, 500 kVA, something like that, or 80 kVA, 20 kVA, something like that. Why is that? Because at the time of manufacturing, the manufacturer doesn't know what kind of load you are connecting. We know that S equal to V times I conjugate, S equal to V I conjugate. I conjugate is nothing but, if I equal to 3 plus J4, I conjugate is nothing but 3 minus J4. Okay. So P equal to S times cos theta. So if, for example, if your power factor is unity power factor, then if it is 100 kVA transformer, it will produce 100 kilowatts of active power. If your power factor is only 0.8, and it will produce only 80 kilowatts of active power. So that is the reason the transformer is always rated in kVA. Now the next topic is, what happens if I connect a DC supply to a transformer? If I connect a DC supply to a transformer, it produces a constant magnetic field. Okay, so the transformer works based on the electromagnetic induction. Okay, so induced EMF V or E, okay, V or E equal to minus N times d phi by dt, where d phi by dt is the rate of change of magnetic flux. If I connect DC, there won't be any rate of change of magnetic flux. It's a constant magnetic flux. So there won't be any induced EMF in the secondary coil. Okay, so no induced EMF secondary coil, so the voltage is going to be 0. So whatever energy supplied by the source is going to be go through the only primary coil. Okay, so since there is only energy consumed by the primary coil, it will act like a short circuit and it will damage the transformer. So never ever connect a DC supply to a transformer. So if I connect a DC supply to a transformer, basically this coil is nothing but an inductor. So what happens if you connect a DC to an inductor? It will act like a short circuit. It will damage the transformer. So never ever connect a DC supply to a transformer. Now we're going to talk about practical transformer. When it comes to practical transformer, there are always power losses in the transformer. When it comes to the power losses, there are two types of power losses. One is iron losses, also called core losses. Okay, iron losses or core losses. Iron losses and core losses, these are constant losses. It doesn't matter, even though if you connect 0 amount of load to a transformer, as long as there is power supply, there is always iron losses. Okay, so these are constant losses. Copper losses, the second losses are copper losses. These are variable losses based on the how much energy you're drawing from the transformer. Okay, primary copper losses, secondary copper losses. Wherever you use copper in the transformer, there are the copper losses. Okay, when it comes to the iron losses, again two types. One is hysteresis losses, another one is eddy current losses. What is hysteresis losses? So these are the core losses, right? So the hysteresis losses happen inside the core. So if you take a core magnetic material, okay, when it is not magnetized, all these little magnets are in different directions. Okay, so magnetically this material is neutral. There won't be any magnetism shown. Whenever I connect to a coil and supply energy, it will, all these magnets are going to be turned in one direction. One side is going to act like north pole, another side is going to act like a south pole. When I connect AC, that has to change direction for every half cycle, right? So if you look at here, say here is the supply voltage or supply current I'm giving. So this loop is called hysteresis loop. Okay, so hysteresis loop tells us the magnetic field so the hysteresis loop tells us the how good is a material magnetically, how good is that material. That's what the hysteresis loop tells us. So here, say for example, okay, there you go. Now whenever the current is increasing, so the magnetism of the material is increasing linearly. Now that is up to this point. Now that's the current is going down, so the magnetic field or magnetism must be come down. So if you look at here, so at this point the x-axis indicates the current, y-axis indicates the magnetic field or magnetism of that material. So here, see, my current is 0, but still there is some magnetism property shown by that material. Here, so the current is 0, but still there is a magnetic field. Now current is going from there to in this direction here. So now the current is negative current. Now the magnetic field becomes 0. So it will continue in the opposite direction and we will come back. Okay, this loop is called hysteresis loop. Okay, so if this loop is really big, okay, then that's a bad material. If the loop is really thin, okay, then that's a good material. Okay, so how do we reduce the hysteresis losses? We can reduce them by selecting a good magnetic material. Now another one is eddy current. Eddy currents are nothing but, say that core is made with the iron, right? So since it's an iron material, whenever there is rate of change of magnetic field placed and there is a conductor, always there is an induced EMF. Because of the induced EMF, there are closed currents inside this core. Okay, there are currents flowing through this core. These currents are called eddy currents. Okay, and because of this eddy current, there are power losses. Now how do we minimize these eddy current losses? So these eddy current losses are minimized by slicing the core. So here, if you look at this core is sliced and there is an insulation between each slice. So that way the core resistance is going to increase. So induced currents are going to be reduced. Okay, most of the times this core is not even a closed loop. Mostly it's going to be L sections, something like this, or I sections, U sections. So core is going to be something like this with I section, and there's insulation here, so there won't be any currents, closed currents. But definitely there are currents right here, there are currents right there, right there, right there. Okay, so to minimize the eddy current losses, we slice it up, put insulation between them and join them together, make it a big core. And the second one is hysteresis losses. To reduce the hysteresis losses, we select a good magnetic material. Okay, so in the next example, I'm going to talk about a practical transformer. So in the next video, I'm going to talk about practical transformers. Thank you.